Well, here's finally the last discussion for experiment number 7, and this is for the third law. And on the third law has a name. It's called the harmonic law. It's actually the one that took Kepler the longest to solve, and roughly 20 years of his life. How'd you like to have a math problem, guys, that took you 20 years to solve? Sounds like a fun problem to me. So basically, what it is it relates how big the orbit is to how long it takes a satellite or a planet or whatever's orbiting to go around one time. We define the period, which is the time for one orbit. Now, for our satellite, I'm going to give you that period. The period turns out to be, just to make certain on myself, 11 hours and 35 minutes. Now you have to convert that into how many seconds, because you'll need to use this in seconds. And the equation for this is this one right here. So it's the mass of the moon times the period squared is equal to a constant 4 pi squared over big G times the semi-major axis cubed. And so that's the equation that you will use to solve for the mass of the moon. In other words, if we're looking at anything orbiting another body, if we can measure how big that orbit is, in this case the semi-major axis, which you already have for this, and you can measure the period, which I just gave you, that has to be in seconds, then you can actually calculate the mass of what's being orbited. It's one of the means that we actually calculate the mass of planets. We look and see how, mass of stars. We see how they're orbiting. We get the size of the orbit. We can measure how long it takes something to orbit, like a binary star system, and from that we can actually get the mass of the stars involved. So what you're going to be doing then is actually we're going to change this to mass over 4 pi squared a cubed over p squared. And don't forget this big G, where big G is known as the universal gravitational constant. We believe that it's related to the force of gravity. We think it's universal, meaning that you'd measure the same amount, and that happens to be equal to 6.67 times 10 to the minus 11, and then it's Newton meter squared per, kilogram squared. But don't worry about the units. This will all come out when you calculate this equation. The units for this is kilograms. And so it's kind of a messy calculation. The way I do this is I go blah times blah squared times blah cubed divided by that equals divided by that equals. And the value should be close to 7.318 times 10 to the 22 kilograms. It may not be exactly that, but it certainly should be in the 22 kilograms. That's a 4, forgive me. 7.348 times 10 to the 22 kilograms. So let's talk about that calculation one more time. So let's stop for just a moment. Make certain you have enough time that this will be on the screen. You can stop this. And then I'm going to talk about again how to calculate this. So let me go ahead and erase this. I'm going to put that equation up one more time. And then make certain you can prepare for this. So the mass of the moon is equal to 4 pi squared over G A cubed over P squared. Remember, A has to be in terms of meters, P has to be in terms in seconds, and know that everything will come out in the right units of kilograms. And I gave you the value of big G. So let me be a little bit more cautious and let you know about this. How do you do scientific notation? If you have a big calculator like this, they have lots of controls, and right down there says double E, right there, double E. And so to write as an example, 6.67 times 10 to the minus 11, the way I write that is 6.67 double E minus 11. And that means that scientific notation. The value of the minus is what's in the parentheses. You don't use the 1 for subtraction. And so, as an example, it's very hard to see in here, so if I would write this, I would write it as, and again, it's hard to see, so I'm assuming you can't see this well. I'm just going to write state it. 6.67 second double E minus 11. And what you get is something strange. Let's try that one more time. 6.67, and now double E, second, double E, minus 11. So there must have been an artifact remaining on the calculator. See that E there. And most calculators have that means for writing out scientific notation. Sometimes, instead of that, you would write down 6.67 exponent, then minus 11. So some, instead of the double E button, has the exponent button. And sometimes you have times 10 to this, and so you'd have to play with this. The way that you can play is, you know that 10 squared is 100. So I would write down 1 times 10 squared and see if you get 100. So play with it a little bit to verify that you know how to input scientific notation if you have a calculator that has that times 10 to an exponent. Every calculator has its little ways of working, so you'll have to experiment a little bit to make certain you understand. So when I calculate this, let's say that in my example, I'm just going to give an example. I'm not going to use the numbers that you use. Let's say that I have 1,000,000 for this and 1,000 for that. So I would have big M equals 4 pi squared times, and so this is how I do it. 4 times pi squared times, say 10 to the 6, 1 times 1.0 double E 6 cubed. Then I would divide that by 6.67 double E minus 11, and then go enter. And then I would hit divide again. Let us say P is 1,000, 1,000 squared, and then hit enter again, and that should give you the answer. In other words, I go blah times blah squared times blah cubed divided by G equals, divide again by P squared equals, and that should give the answer. But you can practice with this. Again, your answer should be in terms of something times 10 to the 22nd kilograms. If you're getting 20 or 21, then it says you're making an error in your calculations. Try it again. Probably that's the hardest thing in this portion is learning how to do this calculation with your calculator. Practice, work with it, and don't give up, and we'll see how that goes. Now, once you get that experimental result, you want to compare your experimental result to the true value. And so what we use there is what's known, I'm going to go ahead and erase this, as percent error. Now, percent error is where you compare an experimental result to the true value. And we do know what the value is. And so what we have here is the actual value, actual true value, again, is 7.348 times 10 to the 22 kilograms. And you have your experimental value. And so what you do is you go ahead, the percent error is equal to the absolute value of your actual value minus the experimental value, everything divided by your actual value times 100. And what that'll do is tell you just how far away from your actual true value your experimental value was. You should be within 5–10% of the actual value. You should be able to get that close with this. If it's above 10%, then you need to go back and double check some of your measurements for like, where would you have to worry about? Your A. Verify that your A was correct. Remember, semi-major axis is A. That's half the length, remember, of the major axis. And it's listed on that table too in the book. And again, explain what is percent error, which is comparing your experimental value to your actual value, and answer those last questions on the bottom of page 97. There is a box on the top of 97 that you show these calculations. If you run out of room, use that portion at the bottom of that page 97, and that will be the last of this. When is this due? The due date here, just double checking the date here, is, well, the day is, where are we at? It's the 28th. April 1st is Wednesday, so it's going to be due April the 8th, Wednesday. If you get it done sooner than then, just go ahead and email me a copy of it. Just scan it and copy it and give it to me. I will be grading over the next week or so lab number 6, and I'll get that back to you. Those of you who had problems in your measurements for that experiment 6, laboratory 6, I will get some data that you can use, and I'll send that off to you in the next couple of days. So keep an eye out for that. Finish up that lab and have it done within just a few days and send that back to me so we have it finished. One last bit of business, and that is our lab midterm. We should have had that roughly now, but with all the disaster and everything we're going through, we're postponing it some. I will email you the details of how we're going to do this and when we're going to do this very, very soon. So relax about it right now, okay? And I believe that now finishes it up, this material that you need for experiment number 7. Guys, be tough, work hard, reread, email me questions. I'll keep an eye out for you. Take care.